When we're doing application, one of the nice tools of exponential function is called a relative factor. In this case, I'm going to let b be my relative factor, which means I can write a formula in this format. A equals a naught times b to the t over n. This can describe any amount, a, over a time period, t. If you know the relative factor, where b is the relative factor over a time period of n, let's take an example. Looking at a bacteria growth. Let's say we have a population of bacteria, increases by 6% every 8 hours. By what population does the sample increase in 3 hours? Well, the first thing what we need to do is write an equation that describes this situation. To do that, I'm going to use a relative factor. Now, we're looking at a population, and we're going to describe our population in terms of percentages. So I'm just going to allow my population of bacteria to be a percentage. So P is going to be the percentage of original population. And T is going to be time. And the easiest time to use for this problem is going to be hours. Now, notice, when we set up our formula, if I describe my population as a percentage, I can say that the initial population is 100, representing that I started with 100% of the original amount. To generate the factor, I'm going to start using a relative factor technique. So I don't have a factor, but I know it's increasing by 6% every 8 hours. So we look at my relative rate. Little r, our big R, is 6%, giving us a little r of 0.06 and giving me a relative factor of 1.06. It is not my factor. What is important to realize about this factor is it does not occur every hour, but my factor occurs every 3 hours.
Isn't that 8 hours?
Every 8 hours, I'm sorry, misread that. So my factor occurs not every hour, but every 8 hours. That makes it a relative factor. So my formula can then be written as the population starting with 100% has a factor of 1.06 every 8 hours. So using a relative factor, I was able to very, very quickly generate an exponential function. Now, answer the question, by what population does the sample increase in 3 hours? Once I have my formula, I can use it by simply plugging in the 3 for the time and plugging that in the calculator just like it looks. Okay. When you plug that in the calculator, we end up with 102.21%, which means in that 3-hour period, I went from having 100% of the original population to 102.21%, or my population increased by 2.21% over that 3-hour period. So, given a radioactive half-life, A radioactive element decays to 50% of the original amount every 3 years. Goal number 1, we're going to write a formula for this element. Since we're not given an original amount of the element, it is common to write the formula as a percentage of the original amount. So I'm going to let P be the percentage of the original amount. NT. And I'm going to let T be time. In this case, the easiest time would be in years. Now, I do not have a rate for every year. It's decaying by 50% every 3 years. So since it's happening every 3 years, I recognize that the n in my quick factor or relative factor is going to be 3. Now I'm going to calculate my relative factor by noticing if it's decaying by 50%, so my R, big R, is 50%, giving me a little r of 0.5 and a factor, relative factor of 0.5 or 1/2. Because it's decaying by 0.5 every 3 hours, or every 3 years. So when we set up our formula, the percentage is going to start off at 100% of the original amount. The relative factor is 0.5, but it does not happen every year. It happens every 3 years. Once we have a formula that describes what's happening with our radioactive element, we can answer several questions about this radioactive element. For instance, we could talk about what is the percentage we have remaining after 10 years. So that's our first question we'd like to talk about. What percentage do we have remaining after 10 years? Notice, P is the percentage that we have remaining of the original amount. So after 10 years, I can throw that in the calculator and find out the percentage we will have. So after 10 years, we have 9.92% of the original amount remaining. Another question I might want to ask, if I'm decaying by 50% of the original amount every 3 years, what is my decay rate for every 1 year? Now, to find the decay rate for every 1 year, I would need to be able to identify the factor, the standard factor, not the relative factor. So to identify the standard factor, basically what we want to do is put this equation and view it in that format where I know my factor B. Because the factor B is the yearly factor. Now, to identify a factor from any given formula, it's very important to note that the input variable is not the factor. The output variable is not the factor, and the initial value is not the factor. That means my factor is everything else remaining, which is 0.5 to the 1/3. This I can plug into my calculator.
1794.
this is a rounded number, but this is my factor, not my decay rate. My decay rate is the percentage that I'm either increasing or decreasing by 1 year off its decay. It's the percentage that I'm losing every single year, or the amount that this number is below 1. So, if I take 1 and subtract my factor, I get my rate 0.206, or, oops, I'm losing it. 20.6. So if I'm losing half of it every 3 years, that means my decay rate is 20.6% approximately every single year. Many times it's easier to work once you have the formula in the standard form, even though it's slightly rounded. I could rewrite this formula now. This exact formula here can be rewritten in the format. P is my percentage of the original amount. I start off with 100%. And here's what I said. This factor on this formula is about 0.794, which means instead of writing it as 0.5 to the 1/3, I can also write it as 0.794 raised to the t. The two ways I've written it are the same formula except for a small rounding error. Because both of these formulas are the same, anywhere I see that I want to work with this relationship, I can use either one of the formulas. Now for me, if I was to ask a question such as, how many years will it be till you only have 10% of the original amount remaining? I'd probably prefer to work with this formula. Let me show you how we could answer that question. Let me just slide this down a little bit, get some more paper showing. And the question now is, how many years until we have 10%? Which means a P is going to end up being 10. If I want to solve this equation, it's very straightforward on how to solve for an exponent. The first thing I will do is remove addition and subtraction outside the parentheses. There is none. The next thing I will remove is multiplication and division. I have multiplication, I will remove it with division. 10 divided by 100, 0.1. Next thing I want to do is isolate my t. I recognize that t is an exponent on 0.94 that gives me 0.1. I'm going to use my logarithm definition to rewrite this as that logarithm. And I will read it as I write it. T is the exponent that we place on 0.794 to get the value 0.1. Problem is, that's very difficult to evaluate. Luckily, if I do a base change, my calculator can approximate this answer for us quite nicely. So I'm going to do a base change to base E. Doesn't matter whether you do base E or base 10. Now I can throw this in my calculator. What do we get? And we end up in 9.98 years. We should have approximately 10% of the original amount. So once we have a formula, whether we're using a quick factor or a standard factor or a compound interest factor, or a continuous growth rate, or a continuous decay rate factor, once we have the formula, we can quickly and easily go from the input to the output, or from the output to the input, simply by solving the equation for the missing value. Let's take a look at this exponential function. A equals 200 times 1/2 raised to the t over 20. What I'd like to do is describe to you everything I can recognize about this function. First of all, let's assume that A is an amount and t is time. If that is the case, then I start off originally with an initial amount of 200. I should recognize whether this function is growing or decaying by determining whether my factor is bigger or smaller than 1, whether it's my relative factor or regular factor, doesn't matter. This has a factor of 1/2 every 20 years, which means I am decaying. So this is a decay function. I'm going to give you the relative factor. One half for n equals 20, which means I will have 1/2 of the original amount in 20 years. This can actually be referred to as the half-life, because I know I'll have exactly 1/2 in 20 years. My half-life would be 20 years. Last but not least, I can determine my annual factor and my annual decay rate. So, by taking my function and identifying the input, output, initial value, everything else remaining is the factor. I'll now plug that into my calculator. 966
Yeah.
approximately, which gives me my annual factor, which gives me an annual decay rate of 0.034, or in big R form, 3.4% annual decay rate.